Okay, we are on the last section, part 4 of the chapter 4 um, on musical sound. And let me dismiss my image. Why can't I find my, there it is. Okay, um, is that the first? Yeah, that's it. Fourier analysis. The Fourier analysis is a tool that allows us to take a repetitive signal, uh, such as a musical tone, or it can be something like a square wave or a triangular wave or a sawtooth wave, and discover the components that make up this particular wave. I've got a couple of demonstrations. Hopefully they'll work, and to show how Fourier analysis works. I may separate, well, we'll give it a try. If it doesn't work, I'll just record it again. But let's get into the lecture. The sound of an oboe displayed on the screen of an oscilloscope looks like this, and they show you here what an oboe would look like. The sound of a clarinet displayed on the screen of an oscilloscope looks like this, and they show you that. Now this is the sum of the two, the oboe and the clarinet together. Remember, I said you don't have a different set of molecules reaching your ear for the clarinet and a different set of molecules reaching your ear for the oboe. It's the molecules are superimposed upon one another, and you're getting one wave hitting your ear, and that's seen in this graphic. Okay, Fourier discovered a mathematical regularity to the component parts of periodic wave motion. He found that even the most complex periodic wave motion can be disassembled into simple sine waves that add together. So you're going to have a fundamental, and you're going to have components at varying amplitudes that will make up the composite waveform. So the most complex periodic wave motion can be disassembled into simple sine waves that add together. Fourier found that all periodic waves may be broken down into constituent sine waves of different amplitudes and frequencies. The mathematical operation for performing this is called Fourier analysis. Let's see, when these pure tones are sounded together, they combine to give the tone of a violin. It's the fundamental, the second harmonic, and the third harmonic, and this is the composite. If you sum all those together, this is the composite. The lowest frequency sine wave is the fundamental and determines the pitch. The high frequency sine waves are the partials that determine the quality, and thus the waveform of any musical sound is no more than a sum of simple sine waves. And with that, I'm going to try to do some demonstrations. First, let me stop the share, and I'm going to focus on my my little oscilloscope here. Let's take it out of. Let's see. You're used to seeing this. You're used to seeing my voice. That's the waveform that produces my voice. And if we put it in spectrum, we'll see that there's a multitude of frequencies. Let's see, where is it? A multitude of frequencies that make up my voice. Here's about 300. Here's 1,000, and I think that's 3,000, and that's 10,000. Right? I can't really see because I'm behind the scope. Now I'm going to. I think you'll still be able to see me because I'm not. Or you'll be able to see the screen. Because I'm not going to share the screen. It's not necessary for me to share the screen. What I'm going to do is I've got a function generator, And the first, this is at 440 hertz. I'm going to play a sine. Oops, I have to hit play. And you can see right there at 440 is a pure tone, a pure sine tone. Now I'm going to make it a square wave. And I believe I told you the last session that the square wave is made up of odd harmonics. So let's see. You can see them. I can't talk while I'm pointing to them, but you'll see the harmonics. And now they disappear. Kind of sounds like a clarinet. Now let's go to a sawtooth. Here you can see that the second is actually higher than the first, the fundamental. This is 440. This is probably about 880, and it's larger. So it's got even numbered harmonics. Now I'm going to go to a triangle. And it's pretty much like a sine wave, fundamental, and then small harmonics. Now let's do the same thing, but switch this. Hopefully it's large enough that you can see. Maybe if I raise this. Let's see. Sine wave. And square wave doesn't look like a square wave. Sawtooth and triangle. Okay, they don't look very good on the scope. Let's go back to square. Oops. No, it doesn't really work that well. Okay. Now, hopefully you've been able. I couldn't see it because I was looking at the signal generator, but hopefully you could see it. I'm going to go back to the share, and I think the important thing was to see that for different functions, the sine wave was pretty much a single tone at 440 hertz. The square wave generated a whole bunch of odd harmonics, and the triangle wave a lot of even harmonics, and then the triangle wave was pretty much like um, a sine wave. There were a few higher order fun harmonics in there, what the book calls partials. Let's go back to the PowerPoint. Oh, before I go to the PowerPoint, there is another share. This is a Mathematica script that I hope I have it. I always lose these things. Let's see. Mathematica. I don't see it, did I? Firefox. Oh, it's not up. Sorry for that. There'll be a bit of a delay. Well, let me go through the rest of um, the lecture, and then I'll get back to the Mathematica. As a matter of fact, while I'm doing that, I'm going to launch Mathematica, um, and get back to the okay, digital versus. Well, I can't read that because it's there's something covering digital versatile discs, digital DVDs, versatile discs. A phonograph record output signals like these. Very, it's called analog, an analog signal. The oboe and the clarinet together. We saw that on the previous slide. This type of continuous waveform is called an analog signal. The analog signal can be changed to a digital signal by measuring the numerical value of its amplitude during each split second. Now, I told you before that I used to work in a recording studio. I worked in the recording studio from about 73 to 75. I was a technician. New equipment was coming out, and everybody was like, well, analog is the way to go. There's no way digital can reproduce the clarity that you get. Well, at the time, the digitizers could only digitize up to 8 bits, and you didn't get the resolution that you needed when you digitized. So everybody poo-pooed digital sampling. Well, little by little, the hardware you could digitize 12 bits, and it sounded a little bit better. And then all of a sudden, you could digitize 16 bits. You could divide this signal into finer and finer detail, and suddenly the digital reproduced the signal better than analog. And with some of the software techniques, you could filter out noise. There was so I was around during that transition where everybody said no, analog is the only way that you can faithfully record music. We used to record it on tape. I could give you a whole lecture on how the little magnet, as the tape goes across the magnet, arranges the tiny magnetic fields on the tape so that when you play it back, the read head reads the orientation of the little magnets and reproduces the sound. But I won't do that. So this was during a time when I worked during a time when the transition was taking place. I lost my cursor. There it is. So microscopic pits about 1/30th the diameter of a strand of human hair are embedded in the CD or DVD. The short pits correspond to 0. The long pits correspond to 1. So whereas when you only had 8 bits to reconstruct the signal, it was very coarse. It was like if you look at some early animations, like Pac-Man or something like that, the animation is very crude because the digitization was coarse. But nowadays, you look at some of the modern video games, and it's very realistic looking graphics with very realistic looking physics behind it. When the beam falls on a short pit, it is reflected directly into the player's optical system and registers a 0. When the beam is incident upon a passing longer pit, the optical sensor registers a 0. So the beam reads the 1s and 0s, the digits of the binary code. Well, if you could only represent a signal by 8 bits, that's kind of crude. But if you can represent it by 16, and I don't know I don't know what the technology is today. I've been out of the recording studio industry for quite some time, but I don't know if it's 24-bit or 32-bit. It wouldn't surprise me. Maybe even higher than that. With that many bits, you can reproduce the sounds very well. Okay, and that's the end. So now that we have that, let me see if I can um, open recent. Uh, let's see, there it is. It may take it a while to load. Let me enable the dynamics. I know you're not seeing this yet. I have to uh, prep it, and now we'll do it. Let's stop the share and let's do a new share. And once again, I can't find it, but I know it's there. Mathematica, here it is. Now, this is my attempt to produce a square wave. You can see here, this is the part of the wave. It's like we're looking at one cycle of the wave, but we're only looking at part of it. So this is kind of a flat. This is would be the vertical, and here's the rest of it. Now it's made up of several different vectors, and they all add one to another. This is my attempt to kind of explain what Fourier analysis is. So let me get the little cursor, and you'll see as we move this around, the all of these little vectors, which are all of the harmonics, they travel around. Uh, they travel around and form the sum of them. Let me stop it at a point. Let's see. Let's just raise it just a little. Let's see if I can. Let's see. Did it do? Yes, 1600. Okay, it should be fine enough. Let's. If we do it in steps, you can see that here's the fundamental. The fundamental is going to go around once. Then this is the third harmonic, the fifth harmonic, the seventh harmonic, and the ninth harmonic. So you can see that they vary in sizes. Now I'm not gonna test you or give you homework to this detail. This is just my best explanation to you of how Fourier analysis works. You've got the fundamental and these other harmonics. As we keep moving, so if we were to follow it, this blue one goes around one time, the green one goes around three times, this one goes around five times, this one seven, and this one nine. It's a little hard to follow, but as it rolls around, that's what happens, and that's what forms the square wave. It's not moving as fast as I want, but I'm afraid if I put it in play, you won't see it at all. Let's, oops, what happened there? I may have made it too fine of steps. You can see how that lavender one up at top, which is the ninth, it's going to roll around. Well, let's just put it into play and see what happens. It may not. Oh yeah, it goes too fast. But anyway, it's what's it's a little. It's just catching it at different parts. Um, let's pause it. Let's try moving it with this one. Oh, it's starting to mess up, and it's just gonna be formatting it. But that's basically the idea of what how Fourier analysis works. You have the fundamental, and you have these different different harmonics is summed together to form the signal. You can see there it's going around there. You can see the lavender is going around, and they're all going around at their different rates. The third harmonic 3 times, the fifth harmonic 5 times, and so forth. Okay, so let's stop the share, and I think that's it for this lecture and for Physics 1305. I hope you enjoyed it.